Morning. Morning. I don't have the test with me, so it's coming back tomorrow. The test that we had last Thursday. I'm demonstrating it, so tomorrow I'll hand it back. So today we're gonna continue with structure 7. This is one of the 7.3 questions. It's a shell method question. Right, we want to use the integration to calculate volume. And this is the volume of solid of revolution obtained by rotating the bounded region between y equal to x and y equal to x squared about the line x equal to 3. So we are slowly moving to the line of revolution may not be x-axis or y-axis, sometimes it's some other line, but we keep it either vertical or horizontal. Because if we put a slanted line for the revolution, the shape is going to be even further. At least, for example, if you have y equal x as your line of symmetry, then you probably have to have the radius. The radius calculation will be much more complicated instead of just x. Right. Let's look at this calculation. This is not a complete calculation. You're just supposed to set it up properly based on the shell method. Let's see a raise of hand. How many of you are graphing when you were calculating this question? Do you graph the shape? Raise your hand if you know how to graph it a little bit. You don't have to be good at graphing, but I think graphing definitely gives you like a way to look at things differently. If you just think about it, to me, if I only look at the equation and think about the shape, it's hard to imagine which one is higher, which one is lower. A y equal to x, it has a 0, 0. X equal to 0, y equal to 0. Y equal to x squared also has a 0, but which one is higher than the intersection? Right, when you try to find the height of the shell, you have to take the top y value minus the bottom y value. Which one's taller between the two? The root or the square? Which one? The root is bigger, right? Because you see we're integrating between 0 and 1. For number that is smaller, x of x actually bigger than x squared. Because if you get a small number between 0 and 1, you square that number, it's getting even smaller. So x squared is smaller. But if you root a number that is between 0 and 1, that number root of x is actually bigger than x, and then bigger than x squares. Yeah. So this is something you can think about it numerically, but the better way is actually graph it to say this which function is higher, which one function is lower. So we are having students today. You guys already have the link. So let's try to graph it to get a better idea of what was the relation between the curve. let me try one. So function. Okay, so first here we'll graph the two-dimensional shape and then think about the revolution. So I would recommend drawing these two curves as a line x equals 3, just to get an idea of how things work. First we'll need the x-axis, so y-axis. Then we'll need the root function. Right, and then we need the square function. Square function actually is positive or negative, but since we're looking at intersections, this is what we are. So that's the region bounded by root of x and x squared, the pink part, and then we have a line of symmetry. These two, they will have two intersections. One intersection is at 0, 0 here. The other intersection is at 1. 1. So if you want to try to draw the line, this x equals 3. That's 1, 2, 3. At x equals 3, you draw a vertical line. That's what we call x. 3. So it's a line. And then we're rotating about this. So the rotation, the way I draw it. And this one also take all the space. If I have to rotate all the way back here, it's going to be on the paper. But that's the idea. So we're trying to use a shell method. What's the shell method exactly is you draw a slice of the shape. This is a rotation. And that vertical slice rotate and end up being a shell, a cylindrical shell. So we are trying to find the volume of that layer of shell, which will be 2 pi r times h. That will be the surface area on the sides. And we want to have that r. That's the thickness of the shell. We're integrating this. The integration, since the integration variable is in r, so size with radius is what you get. And in our case, our radius based on x minus x equals 3, our radius is equal to, you look at the comparison between your line of symmetry and the shape. Shape is to the left of your line of symmetry, so your r should be 3 minus x instead of x minus 3. So x and 3, it's a comparison between the two. Basically 3 is at the center, x is your free variable. This is 3, that's the x that was on that slice. So the distance between the two, this 3, which is this long, this is actually 3, and then the x is so small. So you take the 3 minus x, that's your radius. The radius is 3 minus x. That's how long that is. So first we identify the radius, and then given the radius, we will realize how do we represent the height. Since the radius is supposed to be perpendicular to the height, and the radius is related to the x, and then the height will be related to y value. Actually, you can think of the height over here. It will be the top y value minus the bottom y value. So we should really write y on the top minus y on the bottom, right? And the y on the top is this value that was on the root. So it's really root of x minus x squared. Bottom is square function. So that point is on the root, and this point is on the x squared. If you want to find the y value between the two curves, you take the top one minus the bottom one. Kind of like when you're trying to find area of the curve, except now we're finding this in that vertical slice of the shell. We want to find out how tall the shell is. So that's this H part, and essentially since R is related to the X, this dr is gonna be dx. D it represents differential, so the change. So the change in your R is being determined by the change in X. So we'll just write dx. And that also is how we determine the variable for the integration. If it's dx, then x is go from 0 to 1. 0 x. So the shell method for the volume calculation, follow this formula, so you've got to make sure that the variable is being like little by little, you have to have every piece exactly what it's supposed to be. So this is gonna be 2 pi, and see that's the R, and then this is your H, replace the R and the H, replace the R by the X. And that you kind of have to piece them together to get the right answer. I think maybe halfway when we're trying to look at the picture, you start realizing. Let me go back to that page so you can see whether your answer is being recorded. Okay, so once your answer is recorded, we're going. It was really bright there, so it stands. Change the direction. Okay. No, that's not the one. Okay, so, let's go back to. Okay, that's right, thank you. All right, thank you. Sorry. So we can still, let's try to finish writing this. 2 pi r is 3 minus x, so this is 3 minus x. And then h is root of x minus x squared. And then dr is d of 3 minus x. It's actually negative dx, but normally we'll just write dx. Okay, so all we have to do is maintain that volume is a positive measure. So that's positive, 3 is bigger than x, so that's positive. H is bigger minus small, that's positive, and dx. If you go from 0 to 1, then dx is also positive. So then we guarantee that the final calculation of the volume will be a positive measure. But if it's actually okay, if you accidentally put the wrong symbol, the contrast is not. Okay, that worked. So even if we accidentally have a negative answer, we can always switch the sign, since knowing that volume is supposed to be a positive measure. Right. So I have reported all the answers. Our answer is supposed to be C. So that was the formula for the communication. This question, the main difficulty is in setting up the volume. If you have that information already correct and you multiply them out and then use power rule to finish the integration. So the main difficulty is in the setup. Do you have any homework questions you want to try before we start today? Three, the shell message. Haven't started yet? Is it because you were getting ready for the test? Okay. Okay. So that's the calculation of the volume using the shell method. So far, we've learned 2 different methods for the volume of the ocean. If the volume is created by a revolving around a certain center, and there are 2 ways to handle this. One is the discussion washer method, and the other one, which is you have light slices the volume. And the shell method is you have curved slices, where actually revolve one piece and revolve another piece and get a layer and layer of shell. We calculate the volume of every shell instead of calculating the volume of every disk. So it looks different in the formula, but many times when you use both methods to do the calculation, your final answer is the same, whichever method you're choosing to apply. I think we've done most of the example in 7.3. If you see any difficult question in the assignment, you can let me know. Kylie, have you seen anything you wanna ask? Since you're the one started.
I remember hearing here and like it was.
Okay, yes. Anyone, if you're online, you can also speak with your microphone. Okay. Right, you said number 17.
Yes, the last.
All right, when you look at the question first, we want to know the shape, like left and right, up and bottom. So you can see the y equal to root of x minus 1 should be the up, and then y equal to 0 is the bottom line, and then the rotations about y equal to 3, and then x 5. There's 5. 5 is under the boundary at the right side. So first we will try to understand exactly what shape are we revolving and have a visual view of it. And so let's see the axis. Right, and then we'll draw axis and try to make it black and white. And the function, this function is the root function starting at x equal to 1 to define x equal to 1. So that way, that's the only how it would look like. Y 0 is the bottom line, and then x 5. Right, I made it space if you want 5. 5. So 5, x equal to 5 is a vertical line. That's x equal to 5. The bottom line here is y equal to 0. The top curve is y equal to x minus 1. So we're revolving about y equal to 3. So first we say if x equal to 5, we find that point. This point is clearly 1, 0. So that point is also one of the corner points. If x equal to 5, we put in the function 5 minus 1, root of 5 minus root of 4. So that would be 2. So you can see that this boundary is what we have, a 2. Now we're revolving about this line y equal to 3. The line y equal to 3 horizontal line. And so we're doing this kind of revolution. So this shape, the shape that we're looking at, let's try to. So this one is when we're revolving. That's a 2-dimensional shape, and revolving about that line becomes 3-dimensional shape. Yeah. Trying to get space, so I have space for the. So this is going to be revolved with the y equal to 3 as center line. That's what it looked like after we revolved it. And this is also revolved. We are going to use a shell method. Let's grab a slice of this. This is also revolved, get a smaller center that is also revolved. So you're gonna see a very much similar shape. It look like this. So after you finish revolving it, it's kind of like the outside look like a cylinder and inside have that. That's how the picture isn't good. So 3-dimensional picture always is a little bit of issue there, but I have to draw it just to get the idea of how it works. So with the shell method or the list method, the number one thing is how do we classify, how do we quantify the radius. So it's all about what is the line of symmetry. It says about the line y equals 3. So you're gonna try to look at y and 3 and see which one's bigger. In this case, y equals 3 is over here. Y equals 3 is 3. 3 is high up there, blue. And then the y, which y are we talking about? The y we're talking about is in that pink shape. Every point in that shape is revolved, right? You have a 400 point up there. So anyway, the pink one is where we find all the possible y value that is included in the relation. So all the y value that I was talking about is between 1 and 2, but they're all smaller than the 3. So between 3 and y, the 3 is bigger. So how do we compare them to find the center and edge? 3 is at the center, y is at the edge. So if you want to find the distance, you have to take the 3 minus y. The difference between the 3 and y, 3 being bigger, 3 minus y. That is how you remember you're going to revolve it. So the radius is distance from the edge to the center. The center is 3, the edge is y. So we have 3 minus y, just so that r will be positive. So our radius is quantify that r equals 3 minus y. Since we are trying to maintain that r is a positive measure, radius is a positive measure. Now, once we realize the radius in this question is related to the y value, so we know the height in this question has to be related to the x value. So our h is going to be x related. So in fact, this is our h. The height of the shell, meaning if you revolve, you get a little cylinder shape with all the points being revolved. So that's our cylinder. The height of the cylinder is now horizontal, and the radius is actually vertical because they're perpendicular. So our height is going to be the bigger x max value minus the smaller x value. So it's going to be the x on the right side, the bigger x value, minus the smaller x value. So the x value on the right side, okay, so I mean, if you look at that pink shape, that's really how we get the height. This is on the right side, which is really that's x equal to this x equal to 5. That was on the far right. So this is x equal to 5, and so that's xr. And then on the left is on this corner, and that will be on that root function. So the root function goes y equal to root of x minus 1. But we want the x value in that root function. X, so you have to square both side of the equation, y squared of x minus 1. So then x is equal to y squared plus 1. So that's our y value. So it's going to be y squared plus 1. That's the XR. How do you agree? So then we subtract them. XR minus XL is 5 minus y squared plus 1. So it's 5 minus y squared minus 1. It's actually 4 minus y squared. That's our H. H is 4 minus y squared. Okay, and then with R, we also gonna have dr, since R equal to 3 minus y, so dr, we're gonna do dy. Since we are trying to control the direction of the y. Any questions so far? All right, so I think we have all the quantity ready. Now let's look at how we model the volume calculation. So volume equals, using the shell method, is integration of 2 pi r. It's a shell of 2 pi r times h. It's a shell, and we multiply the thickness, which is dr. Now, with our identification, the r is 3 minus y, so we have 2 pi and then 3 minus y. And then we have the h, which is 4 minus y squared. And then the dr actually is dy, so we go dy. And then we have to figure out where the y value is. It's all the pink part that you find all your y value. Smallest y is at 0, highest y is at 2. So 0 to 2 is our integration. Okay, that finish all the, I think it was 4 minus y squared, I forget to square the y. Actually, square. So square. So sometimes I forget to write it. So that's really how it's set up. Okay, the rest is a polynomial, right? You can take out the 2 pi and distribute it, and then I think it will be a degree 3 polynomial. Any other question? This,
Where did you get the bounds from? How did you find it?
it's from the solid revolving, so we're trying to find the boundary for the y value. So in that solid shape, the lowest y value is 0, the highest y value is 2. Yes,
Explain how you solve the height.
which one?
The height of the woman.
The H, right? The H. So it's the revolution. We're revolving it this way, slice by slice. So if you slice it horizontally, we're revolving this. So the height of the shell. So if you revolve it, it looks like a cylinder. When you see H is really the height of the cylinder. So you have that circular revolution, but here is a perpendicular to the radius. It's the H. You're gonna take this corner, this end minus that end. So the right end minus the left end, but it's the x value. This is the x value, and that's the x value. So you're gonna take this x value, which is 5. So it's 5 minus, and then you're gonna find that x value. That x value is on the root function. The root function is y equal to x, root of x minus 1. You square both sides of the equation is y squared equal to x minus 1. And then x equal to y squared plus 1. So the left side, this x value is represented by y squared plus 1. This x value is represented by 5. So you're going to take 5 minus y squared plus 1. And combine them, you have 4 minus y squared. Because 5 minus y squared plus 1. So that's why we have heights. The height is being represented by the y value. Any other questions? So this is question 17. It takes practice. I understand that for all the volume calculation, every question have its own scenario. What was the outside function? What was the axis of rotation? What was the upper boundary, lower boundary? So they're all different type of question. That's why the integration is different, and we have to look at them case by case. That's why I'm trying to introduce a slightly more abstract formula, like 2 pi r h dr, just so we will not be bounded by a certain like dx or dy method. We're just trying to make it as applicable as possible. That's why the formula itself is abstract, but when you apply the formula, as long as you identify every geometric, if geometric measures representation, then you'll be able to write the right calculation out. Any other questions? So that's another application of integration method, which is the shell method for the application. So if there's no other question, I'll start section 7.4. So today, the new material is from section 7.4. All the class PowerPoint files are already reviewed. Just into this. Okay. Okay, so as you imagine, the whole chapter 7 was to apply integration to solve this or that question. Many of the questions are geometric related. We've done area, we've done volume. So 7.4 is about arc length and surface area. So we're looking for a more specific calculation, and these two are together. It sounds like they're different measures. One is distance. Arc length is sometimes it's called curve length. So you get a curve that says x equal to 5t, y equal to t to the 6th power, t from 0 to 5. How long is that curve? So that's one type of question. Sometimes you will given a curve, you're gonna find out how long the curve. For example, you may have like y equal to x squared. let's calculate the distance from x equal to -1 to x equal to 7. So how do we find the length of it? It's not a straight line, it's not a circle. When the line, when the curve or the arc is randomly defined, it's hard to find how long it is. So that's kind of like finding the path of 2 points on the map. And then calculus kind of help that, as long as you have a formula of conversion. Another one is surface area calculation. And we've done area calculation. We can find area between two curves. And that is assuming you have one curve on the top, one curve on the bottom, the whole area itself is flat. But here we're talking about surface area. For example, maybe it's surface area of a vase, or maybe a surface area of a globe, small part of the globe. So if the surface area is being arbitrarily defined and it's not flat at all, then that's when it's slightly harder than a flat area calculation. All right, so as usual, whenever the questions become random, and what we first started to do is try to model it with a simpler, easier way. So what we can do is you have something, let's see, we want to find the length of a parabola. And it looks like y equal to, looks like one of the sine function, like y equal to sine of x. So we want to find is the curve 0 to pi. So what we can do is we can separate the curve by the look of it, because y equal to sine of x looks like it's going increasing and then decreasing. So we can splash it out. Let's look like a line. So we, instead of calculate the distance of the curve, we can calculate from that point to that point. Right, and this part looks like a line. Instead of calculating that curve, we can approximate it with a easier calculation. Distance between 2 points is equal to the calculation. So we find this point to that point, this point to that point, this point to that point. So we separate the whole curve into 4 different line segments. And we can calculate line segment of every part and add it all together. So one of the ways to handle calculation, the length of the curve or arc length, is to roughly approximate it with straight lines. In straight lines, the distance is easier to calculate than a curve. So it looks like this. So we have the summation, and you can see the change of the x value, which is this part, square, plus the change of y value, which is this part. This square plus the square equal to this square, and then you take square root, that will be the first piece. And you do the same. This is delta x, this is delta y, delta x squared plus delta y squared equal to that distance of that part. And we can do the same for everyone. Of course, the delta xi and delta yi is not the same for I equal to 1, 2, 3, 4. Four different xi, 4 different change of x, 4 different change of y. But the overall idea is to approximate the entire distance from 0 to pi along the curve in 4 line segments. That would be initially the idea, but let's try to imagine how do we make it into a calculus. Well, let's try to connect them with our calculus option. And first is distance calculation or segment, right? So when you look at it, this, I guess we talked about. This is a delta x1, changing x, the first change in x. This is delta y, changing y, number 1, right? If you have delta x1 squared plus delta y, y1 squared, you get this. Now this will be delta x2, changing x, number 2, the second change. This is the second change of the y value, the delta y2. And then you square this one plus square this one. You have this square. Take square root, you have the length. So essentially, this kind of calculation, you have to do it 4 times because we are dissecting the entire curve into 4 line segments. And we're calculating line segment for the purpose of calculating the total distance, right? So idea is that maybe we can have more than 4. Maybe we make a even more detailed, like we can go from here to here, and then to here, and then to here, and then here, and then here. So if the n if the number of line segments gets more, then maybe the calculation of the total distance will be better. So in the end, we think of it, the limit of the n goes to infinity. So n goes to infinity in that summation of I from 1 to n. When there's many, many small line segments, this limit value of this total sum will become a Riemann sum, and that is the limit value of the distance calculation will be much more accurate than having finite number of line segment that we're adding. All right, so how do we make this into calculus? What we can do is we divide this by, we find a common factor of delta x. So we divide this by delta xi squared. Divide this by delta xi squared. And if you divide, you will multiply. So you multiply a delta xi over here. And the reason for this is as n goes to infinity, delta xi gets so small. So when this is super, super small, that it becomes this small change of the x value, that will be the dx. So this is a dx. Right here, this notation combined into our integration notation. And over here, the delta xi over delta xi squared, this square over this square is 1. 1 over. Now that when the delta xi become dx is dx, so that when the dx is super small, the dy is super small because of the continuity of the curve itself. So now we have dy over dx, and that is being squared. So many of the notation is switching from the Riemann sum idea to the continuous version of summation, which is the actual integration. So that one over this is where we get the 1, because that division we have to multiply out to balance it out. Essentially, it's the same thing. See that one under the root will be a square. So anyway, this is how we come up with the length of the curve calculation. The fundamental reason for the length of the curve calculation is Pythagoras. Because that was Pythagorean, so this is Pythagorean, therefore this is also Pythagorean. And going back to, I'm just trying to explain like the source of ideas, the reason that we have our length of curve formula. Now, I was writing dy over dx. dy over dx is the same thing as f prime. F prime of x is the derivative of the function. Dy over dx is also the derivative function. So to find the distance from point A to point B on a curve, what you're going to do is you find square root of 1 plus the derivative square root of x. So you find the derivative, square it plus 1. Square root of that. That's how we find the distance. The reason for the formula itself is Pythagoras here. Any question? All right. We also give it a special name. This thing have the one of the reasons that this arc length formula become introduced together with area, because we would use this notation again. So right here, this notation, this one, we gave a special name. We're calling it ES. The arc length differential. ES is equal to 1 plus f prime of x square dx. So what do we introduce that? This is also called S. S equal to integration of ds. Anyway, all right. What do we talk about this? You can get a curve like this, all right, and then a small piece of it, super small piece of it. It's not horizontal. If it's horizontal, it will be dx. It's not vertical. If it's vertical, it will be called dy. So it's like any kind of direction, could be going down, could be going up, but along the curve, it's gonna take on different value. The ds sometimes is positive, sometimes it's negative. I guess the slope is positive, so then the x could be negative. So we were using the ds just to represent that small thing, super simple, super small. As you can see, ds is this differential, this derivative multiplied by the dx. So it's the derivative times the dx. You can also think of this function as a derivative of the arc length. There, S is kind of like the length between A and B. So it could also be representing the distance from any two given points. You can think of S as a variable. So ds dx will be that. This is something we'll come back again. So whenever you want to represent something along a curve, small piece of the curve, we'll be using this differential. So, and that's what we're gonna use in the area calculation, the surface area. Right, but first let's look at a couple examples for the arc length calculation. And the first one is. All right, this is the first example. We're looking at a curve that is f(x) equal to x to the power of 3/2 from 0 to 4. We kind of have to be careful with what kind of question we assign for this section. Because the arc length calculation involves roots of 1 plus another function squared. Whenever we have root function that we have to integrate, they tend to be pretty difficult. Just imagine if we have to integrate 1 plus x to the fourth. Square root 1 plus x to the fourth, integrating that function is going to be really difficult. So whenever there are roots involved, the calculation can be difficult. And our normal technique will be doing a trig substitution. And trig substitution can be time consuming. And that's kind of the reason why we assign the function that we can have small, like we can have an easy way out of it. So if we don't have a way to handle it, it becomes a integration defined function that has no solution. And so that becomes something that's slightly different or becomes something that might go on to a research paper rather than homework assignment. As homework assignment, we're getting something that's normally have a finite number that we can compute. All right, this example, what we're gonna do, we'll follow our formula and then the calculation solution is already there. But if you were gonna start from the beginning, and this is how we gonna go. Scratch. So for example, we will have to follow the arc length formula. Arc length formula goes from A to B. Integration of 1 plus the derivative by the derivative and square that function and then dx. So that's essentially the formula. And to follow the formula, you first have to know the derivative. So given that function, we first will find the derivative is. It's a power function. So using power rule, we have the power have to minus 1, then we have 1 so 4. So that will be the derivative, and then we have to square the derivative. So if you square this function, it will be slightly easier to handle this. When you square something, you square every term. Let's square this. So if you square 3/2, you have to square the 3, which is 9, square the 2. Which is 4. 1/2 squared is power 1, so there's just x. So that's how it looks like for the derivative. That's what it's that. So once you have the square, I think I forget to write down the square. Once you have the square already calculated, that goes directly into the root part of the calculation. So now we can start writing the L would equal to your integration variable is your x, and here it says x goes from 0 to 4, so our integration limit is 0 to 4. Then we have roots of 1 plus 9 over 4x dx. So since we have a formula for the derivative squared, now we have this calculation. So once you write this out, it won't be as difficult. And then we can start saying, think about how we integrate this. This is 0 to 4. It's 1 plus 9 over 4x. This is degree 1. So degree 1 to the power 1/2 and 5 power for the integration. That was the final answer. We'll come back to it after we finish. I feel like this is a little too short. So to do the calculation, we follow the power rule. Right, that's power 1/2. So with power rule, you will have 1 plus 9 over 4x 1/2 plus 1 is 3/2. 3/2 divided by 3/2. So this is because of power. Then we have the coefficient, that one has zero derivative, so we're gonna have the reverse chain rule. So you have to divide the 9/4 because that was the coefficient for x, so that 9/4. Right, that's the antiderivative for the whole thing. I'm gonna plug in 0 and plug in 4. Maybe we can, before we plug in, we can simplify this. So the 9 times 3 is 27, 4 times 2 is 8. So 8 is in the denominator of the denominator, which goes back to the numerator. 9 times 3 is still in the denominator. Then we have 1 plus 9/4 x to the power 4 and 0. So if you plug in 4, you'll have 4 cancel with 4, it's 9, which is 10. So that's 8/27. 32. Right, it was 3/2 hour. Okay, like that. Okay, 8/7 and 1 plus 4, 9/4 times 4, which is 10. So you have 10 to the 3/2 hour. That's the upper limit. And the lower limit you plug in 0 is 8/27 times 1. So that will be the actual answer. You can socially factor out the 8/27 to get a slightly line answer. So that's this. So it's 8/27, 10 to the 3. And then you put in the calculator. Answer. So many times when you are looking at the solution from Moodle, they tend to be more concise and they only have some key steps in there. So it's better to write things out and solve from your own perspective. And maybe mine is a little bit messy and fancy. You can try to see how you would interpret it. So I would always try to recommend try to write out your own solution. If you are getting a different answer, you should calculate it there with what the textbook is going to see. Any question? Distance calculation, actually, you can try calculate distance with the distance formula between two lines is the formula still applies. So the length of this formula applied, no matter your function is a straight line, a curve, or as long as you have a derivative. If you can't find derivative, that's gonna make it slightly harder to calculate the distance. Okay, so this is another question. Again, most of the questions are defined perfectly, so the square part is not too hard to calculate. The first one, remember how it is? We have when you find the derivative, the power has to minus 1/2 power. The 1/2 power square gives you a power 1, and then have a degree 1 under the it's not as difficult as having a degree 4 or degree 3. So we try to make the term under the radical. We try to make it possible for us to either square root it or find the antiderivative. Right. So this example, see up there, I was saying pay special attention to how to complete the square under the square root. So we would try to handle the root part, make sure you can get it out of the root, or you can find the derivative, antiderivative. So we're trying to find the length of this curve from x equals 0 to x equals 2. As you can see, the entire 7.4 are the kind of question that when you look at the question, you know we got a formula for that question. So this question says we want to find the arc length, or we want to find the length of the curve from this point to that point. And then you would be like, let's follow the arc length formula. So these are the kind of question that we have a formula as computation that often it's giving us some hard time. Let's look at this question. Right, so the calculation part would be follow the formula for the arc length. Arc length formula says distance from on the curve from point 1 to point 2 should be calculated with using that as my intuition. And in the formula, it was a to b, 1 plus the derivative squared remember the square because I keep seeing students forget square. We forget it was actually per second, so the reason for the square is due to the second there. We have to square the one and square the derivative. Okay, so to be able to do the calculation, we first have to know the derivative. Let's see. We differentiate them one by ones. X squared is 2x, so that's x over 4. The derivative for L of x is 1 over x. So that will be the derivative, and therefore over here we are trying to square that, square this subtraction, so it looks like this. Goes 1 to 2, square root of 1 plus x over 4 minus 1 over x squared. So that will be the calculation. And so we say we're gonna try to pay attention to this. So maybe it come out as a perfect square. So let's look at the term under the roots. If you square x over 4 minus 1 over x squared, let's not add a 1, let's square first. If you square, you have the first term will be squared, so x squared over 16. And this multiplication, the x will cancel. If you multiply them, you have -1/4, but we have to count 2. So you're gonna have the -1/2 in the middle. And then lastly, you have to square the 1 over x, 1 over x squared, 1 over x squared. So that's how it looks like when you have a subtraction being squared. So now let's look at how it looks like if you plus 1. If you plus 1 plus x over 4 minus 1 over x squared equal to. Realize if you add a 1, the 1 will not affect the x squared. It will not affect the 1 over x squared, but it will affect the -1/2. So if you have 1 plus -1/2, it becomes positive 1/2. So this is how it looks like. X squared over 16 plus 1/2 plus 1 over x squared. Okay. So one of the things is try to observe the difference. On top is the square of the subtraction, right? Right. The perfect square formula indicated that if you are changing that minus sign to a plus sign, you will have to also change that minus sign to a plus sign, right? 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 So the top one is a perfect square. The bottom one is also a perfect square, right? Are you okay there? So we can try to observe the similarity between the two. This one looks very similar to this one. They're so similar that we realize that they are actually similar in their extension. So this one actually is equal to, this is equal to x over 4 plus 1 over x squared. So it's interesting, we started out with a square plus 1, but then when things are combined, the middle term being a number plus 1, a positive 1, and that actually equal to another square. So what it looks like another perfect square, now it actually equal to a perfect square. And this something is very important because if the term under the root is a perfect square, then the square root will be canceled by the perfect square. So it looks like this. So after we identify that pattern, this is to 1 to 2 square root of x over 4 plus 1 over x squared dx. So we realize the term inside the root actually is a perfect square, and then the perfect square will we cancel the roots, and we actually have this. It's actually 1 to 2 x over 4. Now no more root and no more square because they basically cancel each other. And we have this. And we integrate this x over 4. You bring the 1/4 to the side. X itself is x squared over 2 with a power rule. And then the 1 over x is a derivative. Antiderivative 1 over x is? What's the antiderivative? The natural log, yes. But we don't do the opposite. On the exam, the first question have natural log. Many people think the L of x has an antiderivative 1 over x. It's not. L of x derivative is 1 over x. It doesn't have an antiderivative 1 over x. So we kind of have to remember the relation. Okay, so that's the antiderivative. I'm going to put in the upper limit and lower limit, the 2 and the 1. The final calculation is giving us 4 over 8 is 1/2 plus ln of 2. Say upper limit minus, if we put in 1, it's 1 over 8. And then altogether you have 3 over 8 plus ln of 2. And I guess we'll use a calculator to finish the rest. Any question? I write really big in the middle, but it doesn't have to be that big. Just want to make a point that it's the reason that the thing will work out, because analyze what's inside the roots allows us to get rid of the root function. Oh, so I had a solution there, but put the solution on the board, but you can definitely look it up on inside our text. It's one of the text. All right. Now, sometimes the calculation can be difficult, and it's not the first time we're talking about calculating integration using numerical method. Since chapter 5, we talk about numerically calculating area. We can do Riemann sum. If the integration is difficult to calculate, you can use Riemann sum. We also talk about the Simpson's method, and then we're coming back to it again. If you remember the Simpson's method, I think it was 1 over 3, and then we have y0 plus 1, 4, 2, 4, 2, 4, 2, 4, 1. And so symmetrical at the beginning and the end, but the middle coefficient goes 1, 4, 2, 4, 2, depending on how many. So the final coefficient will always be 1 and 4, and then 4 and 1. And what this one is. So we're trying to partition the whole curve into several pieces. If you were trying to find area of the length, distance from 0 to pi on the length on the curve, we're trying to find the length from 0 to pi, which is where the question begins. And the calculation involves integration 0 to pi square root 1 plus the derivative. Derivative sign is cosine in that calculation, since it's summation of the 2 squared, and you can't really make the cosine equal to tangent. So it's pretty difficult to do the integration, and we don't have antiderivative for this. So this is why we have to do the numerical calculation. So approximation method, use numerical method instead of analytical method for the integration. For that definitely we're doing numerical calculation. And what we are following is a Simpson's method. So what we're going to do, this is really b minus a over 3. So that's b is pi, a is 0, 0 to pi. So b minus a is pi minus 0. That's the divided by 3. And then over here is all the calculation of each of the y value. So we're trying to partition from 0 to pi into 4 parts. 1, 2, 3, 4, 5 calculation, because we involve the 0. So this is y0. But if x equal to 0, you have root of 2. If x equal to partition 0 to pi into 4 pieces, we have 0, pi over 2, pi, 3 pi over 2, and pi. So we're really separating 0 to pi into 4 line segments. So that's y0, y1, y2, y3, and y4. Any question? I believe the method also works with Riemann sum, but if you're doing Riemann sum, you have to have more. 4 may not be enough. So with Simpson's method, we can have less. So the computation, what people call the speed of convergence is faster. But n equal to 4 or 5 is already pretty close to the true value of the integral. With Riemann sum, you probably have to make n equal to 10 other than just 4. Any question? let's move on to surface area. So how do we calculate area of a surface? And in here, we're working on a surface area of a revolution. In Calc 3, we can calculate any three-dimensional surface area, so it doesn't have to be a revolution. Right now, we're looking at a two-dimensional method, one-dimensional method to handle three-dimensional calculation. Volume is three-dimensional calculation. We're trying to use one integration to do the calculation. The reason for that is because it's revolving, so we have a regular shape, and that's many of the things can be simplified into a degree one, or one variable integration rather than two variables. All right, so what's the surface area calculation? First, we want to form that formula. Over here, we're looking at how do we form that surface. So let's imagine you have a curve, which is the blue one. You are rotating this whole curve about x-axis. Have this revolution. So it's forming, we're rotating the curve, not rotating the surface. If you're rotating a two-dimensional surface, you'll be forming a three-dimensional shape. But if you're rotating a curve, which is a line, kind of like a line, curve the line, that's one dimension. So if you're rotating one-dimensional shape, you end up having two-dimensional surface. We're talking about the surface area, not volume, the area on the outside of the whole shape. Okay, as you revolve, you will forming something like this. So what we're gonna do is the same. Since the whole shape is probably gonna have a curved surface, so it's difficult to calculate altogether. Instead, we slice it into small pieces. So each small pieces, you can imagine the side is like a length of the arc. We're rotating that length of arc with respect to axis. That's the idea. So the surface area follows something similar to the cylinder. The surface area for the cylinder is 2 pi r times h. So what we're gonna do, we're doing 2 pi r times ds. Instead of h, we have, because it's not completely horizontal or vertical, so instead we're making it a slightly big random piece of the curve. ds is what we're using, and that ds part is the reason that we're combining the length of the curve and the area formula for the revolution in the same section. We're using similar calculation, similar notation. Right, so this is really the surface area for that small piece, and you can do the same for every single location on the curve. So this thing has to be integrated. So it's really integration 2 pi r ds. That's the surface area calculation. But realize that ds is root of 1 plus derivative square dx. So the ds itself is big part of the differential. So that differential is a surface area differential or arc length differential. And that's combined with the rest. And that's kind of the reason why surface area is even harder than the arc length calculation. All right, so here is the official formula. And this is assuming we're revolving about x-axis. If you're revolving about y-axis or revolving about some other lines of symmetry, then the thing will also be different because you'll have a different model for your r and also height. That's the thing. All right, so there's two different formula. The top one is revolving about x-axis. So remember our original idea, it was supposed to be 2 pi r ds. So keep that in mind. We try to explain this two formula. And the reason we have two separate formula is because we are revolving about different axes. All right, and this is another reason I really recommend having the r and h notation rather than having the dx or dy notation. All right, so basically our surface area in the formula is equal to integration of 2 pi r, that's one dimensional, times the ds. Okay, and remember what was the ds? ds is equal to that root of 1 plus derivative squared, try to write it short, and dx. Okay, so every part of it, you have the ds. That's ds. That's also ds. They all have the ds. That's ds, that's also dx. But then how do we get two separate formulas because we have different r? The first one is saying we are revolving about x-axis. If you're revolving about x-axis, look at this. Right, if you're revolving about x-axis, and what happened to your radius? Your radius is going to be this vertical, right? So your radius is going to be the y value. And since we got a function, our y value actually x. So that r is going to be what this is the r f of x. So that's we revolving about x-axis. A second scenario is what if we revolve about y-axis? Start y-axis. If we revolve it this way, if you revolve about y-axis, what's our radius? It's this. So our radius, since the axis symmetry is vertical, and the radius has to be horizontal, it's going to be the x value. So in this case, our radius is our x value. And that's why it didn't that. So you can see, doesn't matter if it's revolving about x-axis or revolving about y-axis. You are not changing the ds. For all surface area calculation, we have that root of 1 plus f round square dx. And then depending on the axis of symmetry, axis of revolution, you may have either f of x or x. It's so that made it somewhat set because we already have such a formula follow the same thing, but some part that's not set because you're changing how it's being the axis of revolution. Any question? That's kind of the idea there, and then I'm trying to go through why we have how to do this and how to do that. And this is a question that we had earlier. Earlier we were talking about imagine this one. That if you have to revolve 0 to pi about this is revolving about x-axis of the radius of the y. That we can calculate, right? So let's calculate this one. So it's not as hard as the surface, that's the length. Remember for the length, you have to integrate from 0 to pi square root 1 plus cosine x squared and dx. And that we have to do a numerical method because there's really no analytical formula for the antiderivative. But for the surface area, I think we can because we have something else outside roots. In my head, I'm thinking about the calculation difficulty to see if it's doable and analytical. All right, for this one, it's a calculation of surface area. Once we reach that name, you will be thinking about the way to remember the surface area formula. Only on the test, there are different geometric measures that we focus on. So surface area is equal to, now the rough formula is 2 pi r ds. It's two-dimensional. The 2 pi r is this dimension. The ds is this dimension. So they're perpendicular, theoretically perpendicular to each other. So we're talking about revolving about x-axis. That's our revolution. So the radius is this. So this is our radius. Our radius equals the y value, therefore equals sine x. That's the radius. And therefore our calculation is going to be 2 pi sine x, and then root of, that's the ds part. Ds part is 1 plus the derivative. The root of this is going to equal sine x. So sine square of x. Now, this part is something we mentioned for the arc length formula. The arc length differential is ds always equal to square root 1 plus square of the derivative, that was a square. And then the integration variable is x value, and x value is from 0 to pi. So we integrate from 0 to pi. Now it's we can observe that we can integrate this with substitution method because if you call the 1 plus cosine squared of x as your u, then we can find the u. So u equal to 1 plus cosine square of x, then u is equal to, according to power, is equal to 2 cosine of x. Oh, see, negative sine of x dx. I almost felt like that could be the u.
Yeah, you could do like those negative sine x and then do like trig substitute.
Right, yes, so this doesn't work out. Because the change rule, you have to cosine, you also have that derivative of sine. So I guess it's better to like do equal sine itself. You do equal sine of x, then u will equal to negative sine of x. So that would be something that we can solve. So then let's forget about the integration and then just focus on the integration function itself. So we have integration of 2 pi. And this root part is going to be root of 1 plus u squared. And then the sine x dx is the sine x dx. So sine x and dx negative u. So we have negative u. So that's how it looks like. We can still solve it, but we still might have to make substitution. Data. And this is a point I would appreciate having the formula, or if you have some fluency. All right, so but essentially, I'm not one that would simply memorize formula. We have to do this. We get the true substitution. All right, so let's see how we integrate this. If you have to integrate root of 1 plus u squared, you derive the formula yourself, is equal to make u equal to tangent theta. Because 1 plus square theta square theta. So that the u will equal to secant square theta. E theta. And then the 1 plus u squared is going to be 1 plus tangent squared. 1 plus tangent squared is secant squared theta. So under the roots is 1 secant squared theta. Outside root we have secant squared theta. Theta. So altogether, this is going to be integration of secant u theta e theta. And this is equal to, anybody remember the formula? I think it's secant theta to tangent theta over 2. Was that right? You have it?
I remember it like.
We derived the integration of secant theta, and also we derived the integration of secant theta. Yeah.
I never read that. I know
Okay,
how
I
that's.
see, I see. Yeah, I think it was sine theta times theta over 2 plus 1/2 ln of tangent theta plus tangent plus secant theta. Right, this we practiced this in 6.2 when we separate the sine secant to secant square and secant, right? Secant theta, and we did the integration by part. That's why we have the sine theta, tangent theta. But even if you do a integration by part, then you end up having something that has similar term. And you have secant theta on the left, and you have secant theta on the right. You don't have to move it to the right. That's why the division by 2.
And if you would get there and that's something.
Yes, it's secant theta. Thank you. Yeah, all it has should be secant theta. So we switch back to the original variable. U is tangent theta. Then secant theta is, this is your secant theta, right? It's equal to secant theta, which is 1 over. So this is gonna be u times 1 plus u squared over 2, and that's plus 1 over, and you have L, then you have secant and tangent, so that's gonna be u. This is gonna be root of 1 plus u squared plus c. So this is how we are going to integrate this. And then we put it into the original variables. Remember, the u was, see the difficulty there. U is the cosine theta. U is the cosine theta. You put back the u and also put in the negative 2 pi. Then we see the antiderivative with all the results. Let's get this. So it's going to be negative 2 pi. This for the original question should be negative 2 pi times cosine theta, cosine x, and then times root of 1 plus cosine square x over 2, and then plus 1/2 ln of sine x plus root of, remember u is cosine x, so sine x squared and plus c. We should put in the upper limit after we switch back to the original variable, the upper limit and lower limit, they were 0 and pi. Yeah, to finish the entire calculation, you will have to switch back to the original variable, and then back here, you would put in the 0 and pi. So this is a question that's intuitable, but it does take some steps. That'll be it for today. So at least we introduce the formula. Hopefully the rest of you all practice. I'm gonna hand back to them tomorrow. In the meantime, please start the review of chapter 7. A little bit behind on the chapter 7 homework.
And then you have.
And that'll be it for today. Thank you.
You're.